Hello, everyone. My name is Zach with HP Additive Manufacturing Solutions, and welcome to session 4 of HP's Beyond the Layers, a polymer 3D printing series. Here, you'll build a solid understanding of HP's multi-jet fusion 3D printing platform and how our polymer solution fits into real-world production. Each quick 30-minute session focuses on a core topic to help you get up to speed and ready to work with HP's 3D printing technology. So far, session 1 showcased advanced applications in fields such as orthotics, automotive parts, and drone-based wildlife conservation. Session 2 covered the components of Jet Fusion 3D printers, while Session 3 highlighted their scalability for production use. Now, we're continuing our series with our Materials Spotlight section, where we will review the materials HP offers and the benefits of each. First up, you'll hear from HP application engineer Dr. Emily Leaven on the power of PA12 in production. As a reminder, we have the Q&A option at the bottom, so submit your questions and we'll try to answer them at the end or get back to you via email. Now, I'm going to hand it over to Dr. Leaven to get us started. Go ahead, Dr. Leaven.
Thanks so much, Zach. So today we're going to get started talking about the power of PA12 in production, Materials Spotlight. I wanted to start with an introduction to myself. So my name is Emily Leaven. I'm an application engineer at HP. My background, I actually have a PhD in materials science, studied metallurgy, and then when I started at HP, I was on the R&D teams working on material development, agent development, and print modes for our printers. And I did that for a few years, and now I've moved into this application engineering role where I work with our customers and how to integrate our technology with their applications. And in this space, so I come from materials, so I'm our materials expert, and I also focus specifically in the drone space. Although, of course, as all of our application engineers do, we kind of cover every industry. So yes, nice to meet everybody, and please feel free to ask questions in the Q&A, and my email is here as well if you want to reach out afterwards with questions. So for the agenda today, the questions that I want to answer are, why is PA12 the most broadly used MJF material? That's really our workhorse material that's used most broadly. And what kind of applications is it suitable for? So I'm going to start off talking about the value add of additive and MJF specifically. I think in previous sessions, we went into how the process works and why it's the scalable process, but we'll talk about the value add there compared to traditional manufacturing methods and specific within the additive space. And then coming from a material science background, I like to talk about the materials paradigm, which is this structure property relationship for materials. And I'm going to add in an additional layer when we're talking about building with additive of design. So we'll talk about how the process itself relates to the properties of the material, as well as how to use things like computational design to make it to that next level. And then we'll look at some use cases across different industries of MJF PA12, and then leave some time for Q&A. So in comparison to traditional manufacturing methods on the left here, additive in general offers a lot of opportunities for customization, the ability to create new and complex designs, iterate really quickly, and use complex geometries, as well as giving a lot of production flexibility, right? You could be printing one part or 1,000 parts, and then you get a lot of cost and lead time savings often with an additive or an MJF process. But then in the field of additive, if those are the type of advantages you're looking for, that customization, complex geometry, and high mix, where does MJF stand out in terms of additive? That would be in the isotropic part strength, so the ability to create really robust parts that are strong in all directions, the design freedom that it offers, as well as the ability to scale. And so when we look at PA12, this is kind of, like I said, the workhorse material for MJF. And why is that? So first we look at the physical properties of PA12. On the left here, we have the mechanical properties of PA12 on our 5600 series. You can see the strength and modulus are quite high, as well as a really good elongation. for this material and fairly good impact strength as well. We are not quite at injection molding properties, but we do approach the properties of injection molding. So you're able to produce really strong parts. And you have all these additional benefits that come with PA12 on MJF. So PA12 is very recyclable. We're generally using an 80-20 refresh rate, meaning 80% used material each time. That brings costs down, that brings carbon footprint down, as well as having that high isotropy and dimensional control, repeatability of the parts. It's just very fast to be able to print. So all of these things kind of come together and make PA12 our kind of catch-all material. So if you're evaluating a application for additive, because you want those things like the complex geometry, the high mix, or the production flexibility, you would basically start with PA12. And if these properties are sufficient, that's where you would land, because it is a very balanced material. It balances the ability to print quickly and low cost and have that really high repeatability and dimensional control and high mechanical properties. And then you would potentially look for other materials within our portfolio if you needed something very specific. So for example, if you needed a higher stiffness material, you might use the PA12 with glass bead filled, or if you were looking for chemical resistance, something like polypropylene, or of course, elastomers have a completely different set of applications and mechanical properties. And so it kind of branch out from the central point of PA12. The other thing that I want to talk about today is this relationship between the material itself and the material properties, the process. So the MJF process is giving us, with PA12, with the material specifically designed for our process, these really good properties at scale, and then add in the design component of this. Because really what this enables, what having a strong, robust material on MJF at scale enables, is using design tools. So one of the things I'm going to talk about today is computational design. This is a kind of design progression that we show. This is actually a part originally from an HP latex printer, so 2D printing. It's this machined aluminum part where if you talk about CNC machining, the thing that reduces cost is reducing the number of machining operations. That's going to allow you to have a high throughput of parts. But then if you think about this 355-gram part, converting that to just the parts of it that you really need for plastic, that already has a cost reduction and a weight reduction. And then you can go further with complex geometry, like adding this internal truss or lattice structure. And then this is the final iteration of that, where you use computational design, computational tools like topology optimization to basically here you give a computer all of your design constraints, the loads something's going to bear, and it is going to generate, based on those load paths, based on those constraints, a part that has the minimum amount of material required to fulfill those expectations. And so this part all the way here through the design progression represents a 50% cost reduction, 93% weight reduction, and 95 times lower carbon footprint than the original part. And it still fulfills those same demands of the application. So in this case, the computational design allows for optimization beyond traditional possibilities, and MJF with PA12 is kind of the link to being able to produce a part that looks like this that you could not manufacture with traditional means, or would be prohibitively expensive to do so. I have another example of that here using computational design. This is the back post of an ankle foot orthotic medical device. And you can see that computational tools were used here to model the stresses and basically create a more optimized design that's better for the patient, that's better optimized for that final application, and use that complex geometry to have a part that has less mass overall, but is still more stiff in bending and torsion, by taking advantage of those three dimensions. And then the MJF process and the strength of our materials is able to bridge that gap between creating the computational design, creating the CAD model for it, and bringing it into the real world in a way that is strong, reliable, and scalable to fully take advantage of complex geometries. So we can look also at PA12 across different industries. MJF is very prevalent in a number of these different industries, from automotive, a lot of interior automotive components, to drones. I'll focus there a little bit because I work a lot in the drone space, robotics in terms of end-of-arm tools, and even humanoid robotics, or people have probably seen a lot of those robotic dogs. Industrial applications, so we're talking about on manufacturing and processing lines, as well as in O&P and in medical devices or in the medical space. And each of these kind of takes advantage of different aspects of the MJF process and of PA12 itself. So for example, in automotive, it's very necessary to have Class A finishes. And so this really takes advantage of all of the different post-processing that can be done and a lot of the exploration that's been done on MJF PA12. In the drone space, we're very concerned with lightweighting. That lets you go further on the same battery life or carry higher payloads. Yeah, so some of these will take more advantage of certain certain aspects of PA12. So this is the Bushranger drone from the Eye Above project. And this drone has over a 2-meter wingspan and is fully 3D printed. The entire body, the wings, the frame, tail is all printed with MJF. And it's very interesting talking to their CEO. So they're creating this drone for wildlife conservation. It's an anti-poaching drone in South Africa, and it has very specific requirements because of that. It has to survive harsh environment, be field serviceable, has to be really durable and have all those segmented pieces to fit together precisely. And of course, be very lightweight so that it can travel those long distances and stay in the air for a long time. And yeah, Robert Miller, the CEO of the Eye Above project, Telluraves, he was talking about how they had looked at existing drone solutions and nothing really held up to that environment. So they decided to create their own. They tried a lot of different types of technologies, and this was what they found to be the only thing that they were able to really put this drone together and have it work in that environment. And there's reasons for that. There's reasons why PA12 works so well in this environment. So on the left here, I have the part qualities and how they relate directly to the performance of the drone. So you need to have really robust parts with good mechanical properties in order to get that high durability. And the material selection also matters here. So PA12, literally as part of the MJF process, right? You pull parts out of the build and we do a media blast. And that is kind of almost like the sandblasting that this is going to get in sub-Saharan Africa, right? We have to have the repeatability and consistency of these parts in order to fit those segments together. And the really strong parts and that dimensional accuracy, the ability to print those ultra thin walls, which you can see in this top portion here, where you can see the light coming through these extremely thin walls. They're less than a millimeter thick, and then they have this hexagonal ribbing for added stiffness. And that allows this entire drone to be extremely lightweight, which directly relates to performance in terms of flight time, distance flown, or the payload it's able to carry. So yeah, each of the qualities of PA12 here relate to the performance of the drone. And we see the same type of thing in the Blue Flight Cobalt drone and Slate drones. So Blue Flight has two versions here, one with fixed wings and one without. But this entire drone, the body panels, the fixed wings that have an internal lattice structure, and these landing gears here are all printed PA12 MJF, as well as all of these internal components that hold the payloads. So in this case as well, the weight optimization and the ability to have that high consistency and part quality from PA12 is really, really important for this production drone. And in the case of Blue Flight, the ability to paint and do that surface coating is also very important. So when I first met this company at a trade show, even I was unaware that the outer panels of this drone was printed because it was just painted so beautifully. I'm usually quite good at recognizing MJF in the field. So yeah, then we get into all kinds of robotics applications as well. Of course, I can't go into every one of these, but in the case of robotics, we have a lot of those same advantages, the ability to use complex geometries, make robust parts, and yeah, use kind of that lattice or truss geometry. In this case, it also becomes often important to be water and airtight. So, for example, we have some pneumatic grippers where you can pull air through those channels, or some underwater applications. So for example, end effectors that go on underwater drones. And yeah, so those are specific to those type of applications. And you can see here, this is a robotic arm end effector for a painting machine that has these internal channels. Um, and then all the way to something like jigs and fixtures, where you can see this organic looking shape as well. And that's because this has been topology optimized to replace a assembly of metal components. And this part actually has a 2.5 times higher factor of safety than the equivalent metal part, while still having something like a 80% weight reduction. And that's because of how it's designed rather than assembled with stress concentrating points where things are screwed together. So we'll take a bit of a deeper look at the Sodesia example here. That's this end of arm tool, just to kind of show the scale of it as well. So this is a hybrid model where you have aluminum plates, and then sandwiched between that is these black MJF parts. And this is for a robotic end of arm tool that moves car chassis. So with MJF, they were able to have a decreased weight, which this end of arm tool on the end of a robot has a very high moment of inertia. And so if this was all metal and say, 50 to 80%, 50 to 90% higher, higher weight, that is going to just be more dangerous. It's going to have to move more slowly for the robot. And so with integrating the MJF parts on the plastic, they're able to improve performance and also design in features that that can be iterated, changed out. So yeah, they design in features that give them better maintenance, better inventory management as well. But PA12, the plastic, is holding up in these type of applications. I also talked about medical devices. So we have a number of different applications in the medical space, from custom covers that allow companies to be producing parts even in small quantities as they grow, doing prototyping through production, all in the same material. And then something that's a little bit unique in the medical space compared to the other type of applications we work on is the ability for PA12 to be sterilized. We've done testing on different sterilization methods and how it affects the material properties. So yes, it can be sterilized, and we have regulatory compliance, so biocompatibility testing for these materials. So these are used across applications like custom covers, portable handheld devices, the internal mechanisms for this centrifuge, as well as something like surgical guides that are actually used for surgical planning. And then this is also in the medical space, but orthotics and prosthetics. You can see a multitude of applications here, from orthotic insoles, from Arise, this piece here, and to braces, so something like a knee brace. And in this case, this actually is PA12 that's been dyed green. Cranial orthoses, prosthetic covers, so prosthetic leg covers, as well as this prosthetic socket. We have a number of different sockets due to the really high strength. And so in order to get to that high strength that allows it to be less bulky, more customized for the patient and give better patient outcomes. And even applications like a scoliosis brace or prosthetic arms. So yes, this is the cranial application that I was speaking about from Ottobock. So this is a cranial molding helmet printed in PA12, and you can see there's the ability to customize, the ability to just have very good patient outcomes for children where they don't have to keep redesigning or reshaping the part itself. And again, taking advantage of all the biocompatibility, the customization of PA12. And then as a last example here in the prosthetic space, this is from Quorum Prosthetics. This is actually a combination of materials. So the inner liner would be one of our elastomers, and then this outer piece here, which has a lot of complexity to the design, but all of this is so intentional to add value to the patient themselves because they're able to make something that's much more adjustable. It's this really beautiful design, and they also take advantage, since this is going to a final patient, of the ability to post-process, dye, and have a very professional look and feel to these parts. And then lastly, in the machinery and equipment. So I couldn't get to all of even the segments that we're a part of today, like for example, eyewear, but if you have questions about your segment, please reach out and we can discuss it and see if PA12 is a good fit for that. But in the industrial and machinery equipment, anything from camera mounts to this is a very interesting application it twists these cans to put them in a new orientation during a processing line. So these are very kind of industrial manufacturing applications. These pucks that are custom designed for the exact product that they're meant to carry. And I've spoken to people who have tried to use 3D printing or something under the umbrella of 3D printing for these type of applications before, and found that they broke. But the really robust PA12 coming out of this process, again, our PA12 is highly designed for our own process. That these, you just need something that holds up really well in the application, and you're able to create parts on demand and customize for the application. So with that, I'm going to turn it back over to Zach and open up for questions. Thank you so much.
Yeah, perfect. Thank you, Dr. Leaven. I think it's worth stating too, the majority of applications you showed today, there was no additional post-processing, correct? They came out of the printer, printed on PA12. There might have been some dyeing and stuff, but the majority of it was just PA12 by itself, correct?
Yeah, so all the parts that you saw here that were gray parts like this is the standard finish out of the printer after the media blast. But there are quite a few of them that do have some type of dye process. It really just depends. We have a lot of information on different post-processing methods. So anything from dyeing and vapor smoothing, which vapor smoothing is not just cosmetic, it also has benefits when it comes to mechanical properties. You're reflowing the surface, and so you eliminate crack propagation sites in the surface. So you can get enhanced mechanical properties through vapor smoothing, seal the surface to water, and then you can also do coatings like painting, Cerakote, even a UV coating or a UV powder coat. So we've tried a lot of these different things. Yeah.
Yeah, amazing. Thank you. So we do have a couple
So
more minutes if you have
totally
any.
depends on the application. Oh, go
Yeah,
ahead.
no, no, for sure. Yeah. So we have a couple minutes if anybody has Q&A As a reminder, it's there at the bottom to submit your questions. Um, a few questions that did come in. What's the highest temperature that PA12 can withstand?
Yeah, so the melting temperature is up in the 180, 185 C range, and then the heat deflection temperature would be somewhere in the 170s. I have to look up precisely. I think it's around 175 C, but it is dependent on the pressure involved, right? So if it's
Mhm.
under higher force, then that would be slightly lower. So again, depends on the application, but we've even seen people use PA12 as fixtures at higher temperatures than that for short times, right? Because you have a high thermal mass, so it's not going to get to the melting point.
So would it depend on like the thickness of the part as well?
Yeah, so the thickness of the part and time at temperature are going to have an impact, but in terms of heat deflection temperature, I believe it's around 175.
Okay. All right, thank you. And we have another question coming in. This will kind of lead to the additional sessions that we'll be having under the material spotlight section. But why use PA12 over, say, PA11, which is another one of our materials?
Yeah, so like I said, PA12 is kind of our very balanced material. PA11 would be if you need higher mechanical properties, but it is going to have the trade-off of cost. So it kind of depends. If PA12 is sufficient for the application, then you'd stop there. But in applications that require that higher impact, higher elongation at break, then somebody might choose PA11.
Got it. Thank you. Kind of going back to the post-processing that you're showing here. So PA12 will accept a direct Cerakote application, or do you know what the process is for that?
I know there's multiple types of Cerakote, and there's one, so some of them require different oven bakes, oven cures. So I would have to double check on exactly which Cerakote line this is, but I think this does have an oven cure component that's, significantly lower than the melting temperature of PA12. So this is pretty widely used on PA12.
Nice, thank you. And another question came in. What's PA12 made of?
So PA12 is a nylon. So PA11 and PA12 are nylon 11 and 12. Um, I don't know. Maybe we can connect offline if you're talking about things like the exact chemical structure of the material.
Yeah, we can definitely connect via email.
Yeah.
Let me take a look here. There's a question that said, what could be the outcome of using other materials such as polypropylene, P11, or PA12S? That question we'll definitely answer in our upcoming sessions of the material spotlights. We're planning about 3 or 4 additional sessions to kind of review all of our materials. So definitely stay tuned, and we'll go through our different flexible materials, our chemical resistant materials, and the like. So you'll be receiving emails with when those topics are announced as well. All right, so it looks like we're at 30 minutes. So if you submitted any additional questions, we'll get back to you via email. I want to thank Dr. Leaven for presenting today. Thank everyone for attending this session of HP's Beyond the Layers as well. As I said, you'll be receiving an email. It'll have today's replay, a link to the previous sessions, and the registration link for session five's topic, which is going to be Material Spotlight PA12 variants for real-world applications, where we'll discuss some additional versions of PA12 we offer and what enhancements they each provide. But for now, I hope everyone has a great rest of your day, and we look forward to seeing you in the next session. Thanks, everyone.
Thank you.